We're all good? Sure, go right ahead, Carolyn.
I have a tournament on Saturday.
Field hockey?
Yes.
Where would that be? Wow. Traveling big time, huh? Whole weekend? Or just one day? Overnighter or you're coming home? Long day, though. Good luck. Anybody else? Where would that tournament be? Not bad. That's not an overnighter. It's a one-way, two-way. Yeah. All right. Good luck, Evan. This is basketball. Okay. All right, here we go. I'm good, by the way. Not doing much. If you want, no one asked. Thanks, appreciate it. All right. Let's do this. Three-dimensional figure we're going to call a polyhedron. There's three parts to a polyhedron I need you to be aware of. The first part is a face on a polyhedron. Let me highlight what a face looks like. Here's what a face is on any polyhedron. Okay, that's a face. We also have what's called edges. An edge is part of the face. And the third part is a vertice. So F a vertice, H a vertice, E a vertice. So I have a face, an edge, vertices. That's what I need you to be able to identify in any polyhedron I give you. So take a look at my cube in number 1. In number 1, take a look at the cube. How many faces are on that cube? Should be 6 faces. Now, sometimes we get a little tougher because you always, did I count that already? Edges. How many edges on that cube? 12 edges. And then how many vertices on that cube? There should be 8 different vertices. Yep. Anybody know what number 2 is called? What type of polyhedron that is? That's on Monday. We'll talk about it. But for Egypt, pyramids. There you go. How many faces on that pyramid? Don't forget the bottom. 5 faces. Yep. Number of edges? 8 edges. And how about the number of vertices? 5 vertices. Yep. And this is what we're going to start talking about today. Number 3. This is called a prism. Okay, number 3 is called a prism. It's specifically a triangular prism. How many faces on that triangular prism? 5 as well. Number of edges? Ooh. 9, nice job. And how many vertices? There are 6 vertices. Now, believe it or not, there's actually a pattern between the number of faces, vertices, and edges. And do you know who discovered that pattern? Remember our boy back in the day when we talked about circumcenter, orthocenter? He found a famous line, Euler-Euler's line. Yep. He also found a pattern between faces, edges, and vertices. And that's what I'm going to show you right now is if you ever want to check to make sure, because you never know, you may have missed one, may have counted one twice. So if you want to check if you have the correct amount of faces, edges, and vertices, it should fit into this check. The number of faces plus the number of vertices minus the number of edges. Unbelievably, no matter what the polyhedron is, it will always equal 2. Check it out on the ones we just did. Faces and vertices minus edges, always 2 in a polyhedron. Unbelievable. That guy's a genius. Works for all 3 of them, yeah? 6 plus 8 minus 12. Got it, 2. All right, faces plus edges, faces plus vertices minus edges equals 2. All right, if you ever want to check. All good? Questions? All right, now we get to this thing called a cross section. Every year they test it on the Regents exam. Cross section. Here's what a cross section is. You take a polyhedron. Here's my cylinder. You take a plane and you slice it. All right, so let me say I'm going to slice this horizontally. I hold it up to you. What's the two-dimensional shape I've just sliced? Circle, right? Now, is that the only way I could slice it? Is horizontally? No, I could go vertically, right? I could chop this thing right down, hold it up to you guys, and what's it going to be now? A rectangle. Everyone agree with that? A rectangle. Now, me just showing you a thing of Clorox disinfectant wipes isn't going to cut it, right? I want to do this visually because there's other polyhedrons that we can cut. So I would like you guys go ahead, go open up your Chromebooks, and if you could go to this GeoGebra website, and we're going to actually take a look at different types of cross sections that could happen, so you guys can visually see what we're doing here. Yes, sir. We'll be there in a second. Yep, just going to wait till everyone gets there. We getting there, getting there. Some of you guys might be playing around already. Okay, I'm going to go there myself now. Okay, let's actually take a look at those prisms and cylinders. So we can go right here, sections of prisms and cylinders. Let's take a look at the cylinder real quick. All right, let's take a look at the cylinder. And this is awesome because we can play around with it. All right, see right now we're doing a horizontal cross section. So we're splitting it horizontally. You guys want to click on view from the section, it'll show you the two-dimensional shape that it forms, which as we predicted was a circle. Okay, now what if we wanted to go to the vertical cut? All right, what if we wanted to go to the vertical cut? So you can go up here from horizontal, translate it all the way over to vertical, and then view from the section, and it'll show you it's a, everyone see, showing you it's a rectangle. Okay, so again, come on over here, go over to vertical, view from the section, it'll show you what it is. Okay, let's go to cylinders. Go over on the left-hand side here, it says section of cylinders, because this one's an interesting one. See if you can predict it before it even happens. Can I go to cylinder? What's that? What? Oh, not so. I'm sorry. I didn't mean cylinder. I meant cube. Not cube. Yeah, now I'm rattled. Cones. Sorry, cones. There we go. Over left-hand side, right down here. Sections of cones. Okay, so we go to the cone here. Horizontal, what's it going to form, do you think? Horizontal. It's going to form a circle, this is what we have right here. Horizontal, going to form a circle. What do you think if we made a vertical cut? Okay, let's try it out. Vertical cut. Let's see what that looks like from the section, cross section. There it is. Now, the neat thing is in between. Like as I go from, take a look, as I go from horizontal to a vertical, it doesn't automatically stay a circle. Take a look. All right, it's kind of like a little arching effect. Does everyone see that? As I cut almost like a diagonal cut from horizontal to vertical. All right, it doesn't form a circle or a triangle. It's kind of halfway in between. A little arch there. Okay, and if you want to play around, you can go to pyramids, rectangular pyramids. It's up to, just so you guys get the idea of a cross section. Do a vertical one. It's going to be a triangle. Almost a triangle anyway. All right, do we get the idea of cross sections here? Slicing it through a plane, slicing a plane through your figure, and then showing me what two-dimensional object ends up happening. Okay? We all good? Okay, you can leave that out because you can cheat with it right now. I got a couple multiple choice examples for you. Same cross section as a sphere. Which one of these polyhedrons is going to have the same cross section as the sphere? Well, we can go back and look, but what do you think? Any way I slice a sphere, what am I going to end up having? Yeah, I'm going to have a circle. No matter if I do horizontal or vertical, take a look, horizontal or vertical, that's still going to be some type of circle. All right, so going back to that question, which other polyhedron can I get a cross section of a circle from? I can get it from the cone by slicing it horizontally. Okay. And on the next one, we got William, who's going to do a cross section of this cone. Which one will not be a cross section of the cone? This is why I had you guys take a look at the cone. Which one is not going to be a cross section of the cone? Which figure did we not get up here? The square. There's no way. We get the circle by doing it horizontally. We get the triangle by doing it vertically. We get this little arch by doing it about halfway in between, but we never get a square with the cross section. All right. Are we all good? Because now I'm going to go on to some area stuff. All good with cross sections, faces, edges, vertices. All right, here we go. Here's the big topic for today. We're going to take prisms and cylinders, find lateral and surface area. All right, lateral and surface area. First thing, prism. What is a prism? This is huge today. A prism's got two parallel congruent bases. Two parallel congruent bases. So can anybody identify me the shape of the base in that first prism I've given you? Look for the two figures that are parallel and congruent to each other. What shape are they in? They're pentagons. The bases in this prism I've given you first are pentagons. So the bases are equal to pentagons. And that's how we're going to name it. That's how you name any prism, is by what the shape of the bases are. So ready to get fancy today at the lunch table? Pentagonal prism. Woo! If I could spell it. How about there we go. Pentagonal prism. Share that with everyone this weekend, huh? While you're balled up in your corners of your room. Or going to Syracuse or Saratoga. Two types of prisms. There's a right prism, and what that tells me is the edges are perpendicular to each other. This is where we're going to primarily stay, is in a right prism. And oblique prisms, they're not perpendicular. They're kind of, as you can see, like a leaning tower of Pisa right there. All right. Have you guys heard of these two terms, lateral and surface area? Let me start with surface area. What is surface area? Don't tell me the area on the surface. Anybody? What's up, Malin? It's everything. It's the area of the entire figure. All right, the area of the entire figure. So, yep, I'm going to kind of steal what Madeline said. That's the area of all the faces. So what makes that different from lateral area then? If this is the area of everything, all faces on the polyhedron, the lateral area, ready? Take off the bases. Okay? Take off the bases, the faces that are, and it's like a little rhyme time here. Take off the faces from your prism. Whatever faces are left, that's your lateral area. So it's the area of all the non-bases. Okay, the area of all the non-bases. So again, surface area, everything. Lateral area, take away the bases, whatever's left, find the area of that. Okay, I'm going to go backwards here, where I'm actually going to start with number 2 first, and then we'll go back to number 1. Let's start with number 2 first. First of all, where are the bases? What shapes are the bases on this prism? Where are the two congruent figures in this prism? Let's hear from some of you guys. Feeling good today. Feeling good. It's going to happen. Feeling good. Feeling good. It's going to happen. I was almost there. Almost. 17. What are the shape of the bases? Triangular prism. Triangular prism. So let's first, it says find your lateral area for part A. So here's how we're going to find the lateral, everyone. Everybody take off the two triangles. How many faces are left? 3. Find the area of all 3 and add them up. You got your lateral area. Again, lateral area. Take away the two triangles. Find the area of the 3 remaining faces. That's my lateral area. All right, let's go on to the bottom. Let's go to the bottom face. What are the dimensions on the bottom face? That's a what by what rectangle? 12 by 16. So I'm going to go 12 times 16 plus, let's do a second face. What about the face on the left-hand side over here? This left-hand side face, that's a 9 by 16 rectangle. And I purposely left out the one on the right for last. That's a 16 by, don't know. I don't know this measurement. Any way I can find it. Pythagorean theorem. There we go. Just like you never left it. 9 squared plus 12 squared equals c squared. And what is the measurement of that missing edge that I need? When you get it, 12, let me know. 15. So that's going to be 16 by 15. Lateral area. Take away the bases, add up all the remaining faces. So the lateral area for this one, let's see who's on their game if I even have to say anything. 24. I'm waiting. Yes. It's area, lateral area, so square units. Surface area now, part B. Everything, guys. It's everything. You've already done part of the work, haven't you? You know area of 3 faces is what? 576. So I'm just going to take that 576 now, and what should I be adding in? The bases, which are what shape again? Triangles. Go back to last unit. Area formula for a triangle. 1/2 BH, and how many bases are there? So I'm going to multiply it by 2. So again, I'm taking my lateral area and adding in the 2 bases, which are triangles, and there's 2 of them. So 576 plus 1/2. What are the base and the height of those right triangles? Here you go, 14. 9 and 12, the 2 legs. So 9 times 12 times 2, because there's 2 of them. Surface area. What do you got for me, 27?
62,200.
What? Where are you getting that from? 576.
Oh, I did. I multiplied.
You have one job. You have one job. Let's go. Finish it. Let's go. That dye's running into your brain. All right, the only way you redeemed yourself, you got inches squared there. Good. Quick common sense discussion. Which one is always bigger? So I hope the surface area is always bigger, yes. Okay. All right, let me go to 1 now, because there's a little bit of an issue we may have with 1. What?
Would it be that
What's my issue, Frank?
all the sides are parallel?
I have 3 pairs of congruent parallel sides. Everyone agree? I got the right and the left side, I got the top and the bottom, and I got the front and the back. So my question to you is, and your question to me should be, what are the bases then? Which one do I pick as the bases? This is called a rectangular prism. Anytime we deal with a rectangular prism, we're going to follow this rule. The bases are going to be the top and the bottom as it's drawn for me. All right, the bases are going to be the top and the bottom as it's drawn for me. Okay, so in this case, my bases are going to be the 10 by 3 rectangle on the bottom and on the top. Okay, hey, I turn this up. Take a look, take a look. I turn this up. Now I would consider this 3 by 3 square my base. Okay, so for rectangular prisms, the bases are going to be top and bottom as it's drawn. Everyone good okay on that rule? Smooth rule for us all. Okay, so the lateral area then? What are the dimensions of the right and the face on the right and the left? 3 by 3, and I know I have 2 of them that are the same. Plus front and back base, front and back faces, 10 by 3, and I have 2 of them. And I'm not counting the one on the top and the bottom because I'm considering those my bases. And in lateral area, you do not consider the bases when calculating it. What do you got for me, 25?
I got, there's lateral area.
Yep.
I got 78 inches squared.
Yep. All right, now surface area now. I'm going to take that lateral area and now add on those 2 10 by 3 rectangles on the top and the bottom. And I'm not going to ask you that 138 square inches. Look at everybody go. Questions? Ready for a special type of prism? If the bases are circles. A prism where the bases are circular, that's a cylinder. All right? It's a prism with circular bases. And you guys are going to come up with the lateral area on your own. It's about as ghetto as it comes, but it's going to work. Describe to me what lateral area is again. The area of everything but what? The bases. So I took the circles off. This is what I'm left with for the cylinder. Okay, circles are off. How can I find the area of what's left here? Well, if I open this up, what's it going to form? Everyone agree, a rectangle. How do you find the area of a rectangle? Length times width. Agreed? Okay, focus on this side right now of the rectangle. I want you to tell me when I fold this back up into a cylinder what it represents in the cylinder, right? So I'm looking at this length right here. I fold this back up. How can you describe what it is for the cylinder? Right here, ready? Again, looking for that length. That's the what of the cylinder. Everyone agrees that's the cylinder. Okay, so you got the first part down at least. You know, lateral area is going to have to do something with the height. All right, now let's get a little bit more complicated. Let's talk now this side. This is the height of the cylinder. This would be the what? Everyone ready? Ready? Here. What's this going to represent here? This distance around? Circumference formula from 2 units ago. Pi d. So lateral area. Circumference times height. What's the circumference? Pi d times the height. There you go. You just found the lateral area on your own there. Pi dh. Circumference times height. All right, you can also get surface area now. Surface area, I take the lateral area, which I just found is pi dh, and add on what to it now? What do I add for surface area? Add on the bases. What shape are the bases? Circles. I have 2 of them. What's the area formula for each circle? So it's going to be pi dh plus 2 circles, pi r squared. Okay, and this one's not on your formula sheet, unfortunately. All right, not on your formula sheet. All right, let's get through this because I want to get to that very last question. I'm getting jacked up about already thinking about it. Lateral area of this cylinder. Pi dh. Pi, diameter is 10. Now I know people are just going to throw the 2 on for the height because you just see a random number there that's left over, so it's got to be the height. But listen up. The height of a cylinder is always the distance between the circles. All right? Remember that. The height, if there's more than 2 values on there, the height of the cylinder is always the distance between the 2 circular bases, which in this case will be 2. And to the nearest 10th, what are we looking at here? 13, nearest 10th? 62.8. Thank you for the units as well. Okay. Won't waste much more time here. Lateral area for this next one. You guys have pi. What about the diameter here? 6, with a height of 6 as well. $36 pi. Same as rounded to the nearest 10th, 22. Thank you very much. All right, now go surface area. Now go surface area, but leave it in terms of pi. So you got pi dh plus 2 pi r squared. Pi diameter here. 2, that's what I was thinking. Nice job. Height of 3. The only reason I get worried when you use surface area is because you have diameter on one side, radius on the other side. I get a little nervous there. Times 1 squared. Quick question there, honors kids. Can you combine these two? Because it says leave your answer in terms of pi. Can I combine them? 2 pi, 6 pi? Yeah, as long as they both have pi's in them. So it's going to be 8 pi meters cubed. Cubed, settle down. Squared. All right, all on you here, number 6, all on you. Make sure you're putting diameter and then radius where it should go. 18, ready to go?
94.5 pi centimeter squared.
Should get 70 pi for the lateral area. And the 2 bases should have been 24.5 pi for the area of the 2 bases. Questions? Let's go on this last one. This is where we should be. Look at that thing. Cylinder plopped on top of a cube. Find the surface area of that figure. Now, here's the issue. You just can't go surface area of the cylinder plus surface area of the cube. I'm done with the problem. Guys, surface area. Everything showing on the outside of the figure. Are all the faces showing on the cube? No, part of that 6 face is being covered up. You cannot, while calculating surface area, you cannot calculate things that are being covered up. All right, it is only everything on the outside that is showing that counts as surface area. So let's start with the cylinder surface area. Is everything showing on the cylinder, or is something covered up? Describe to me what is being covered up on the cylinder that I cannot include in my surface area. What is being covered up? This base right here. It's on top of the cube. So instead of using, help me out, instead of using pi dh plus 2 pi r squared, which is the full surface area formula, that's not going to cut it. You told me one of the circular bases was being covered up. How can I adjust that formula now? Just do not 2 pi r squared, but pi r squared. Everyone see why I'm getting rid of the 2 here? Surface area. Everything on the outside cannot count what's being covered up. So for the cylinder, it'll be pi times diameter of 4 times the height of 4 plus pi. Radius will be 2 squared. (16 pi plus 4 pi, 20 pi for now. I'll go back and work with that in a second. We okay? Guys, tell me now before, because the cube's going to be a little bit different. Everyone all right why I'm disregarding one of the bases? It's being covered up. It's not part of the surface area. All right, you ready for the cube? How many faces are showing? How many faces can I calculate the area of? How many faces are showing right now in that cube? There's 6 total, but how many full faces are showing? I have 5. Where's 4? I know, but there's 6 total, isn't there? So there's 5 full faces that I can calculate the area for. Okay? So 5 full faces, and what's the area of all of them? 5 by 5. Each one's 5 by 5. So 5 faces that are 5 by 5. Now I need help with that 6th face on top. Because you guys you have to tell me how to find this area right here. Because that's still showing, and that's going to count for the surface area. Suggestions. How I can find what's left over here. What do you got, Nate Dogg? Okay, so I do 5. So I'm going to subtract out. You're saying subtract out or add in. Sorry, add in. Ready? 5 by 5, which is the whole face. But I need to subtract out what? The area of the circle that's on top of it. Everyone see that? It's kind of like a shaded region problem. All right, I'm going to take that area, subtract out the circle, pi r squared. And what's the radius for this one? 2. So again, 5 faces. And this represents right here the 6th face. Everyone see how we're calculating that? 25 minus the circle on top will give me the area left over. So go ahead, calculate that. There are no rounding directions here, so we're going to go Regis rules and write out the full calculator display. 137. Yes, Frank.
Couldn't you just do like 6 times 5 times 5?
Yep. Mm-hmm. Same thing. Yep. And then your total surface area now will be that 20 pi plus your 137. $200.2654825. What do we got? Inches squared. Okay. Are we okay with that? That's where I'm. What's up, Maddie? Oh. Let me just rephrase what Matt just told all of us. My method, 10 times better than your method.
I did lateral area of the cylinder and then surface area of the cube.
Lateral area of the.
For the cylinder. And then I did full surface area of the cube. I guess even that one sidewall to the top. Because when you do the lateral area of the cylinder, it accounts for the minus 1.
Okay. Thanks, Matt. You got 37? Got a compass too? I think 30, I can't, 31 or 37, I cut it off. Big, yeah, 31 or 37. No, probably 31 of your regents. Why not end the week on a strong note with a construction, huh? Yep, 31, everyone.
Is it 37 or
31. Make a tangent line going through A. What do you remember about the radius and the tangent line if they meet at the point of tangency? Perpendicular. So anybody want to refresh everyone's memory how I'm going to use my compass and straight edge to make a perpendicular line going through A? What should I do with the radius first? Extend it more. Yep. So I'm going to take my straight edge, extend the radius more. Where's your compass point going? Or compass, yeah, where's your compass point going? Should be going on point A. And what are you trying to do with your compass now? Make an arc that intersects twice. Where's it going from here now? Goes to each point of intersection. And make sure you read the directions. It says draw a tangent line, not a segment or a ray, a tangent line. All right. All right, not many this weekend.